Hello, welcome back to the class. Today I am going to start module 3. So module 3 is about limit state design of beams. See, in module 2 it was limit state analysis of beams. So what is the difference between those two? In case of limit state analysis of beams, you were given a design beam. That means the beam which was already designed, that means the dimensions were fixed, reinforcements were calculated, stirrups, bent up bars, all those things were calculated and they were provided accordingly. So what we did was, in the previous module, we calculated the design moment capacity of the section and also design shear strength of the section. Okay, based on those values, so in some of the examples we solved in the previous problem, we calculated, so what was the maximum service load we could apply. Okay, so that's what we did. So in this module, in limit state design of beams, we go in the reverse direction. So as structural engineers, this is what you are supposed to do, not the analysis, instead the design. So what is a design? Just it is a matter of finding out what are the dimensions of a section needed, okay, and also how much reinforcement you need. If it is a singly reinforced section, how much tension reinforcement you need. If it is doubly reinforced, so how much tension as well as compression reinforcement you need. And if it is T section and singly reinforced, it is again tension reinforcement, and if it is a T section with doubly reinforced, so both compression and tension steel with, of course, with certain width of flange. Okay. So in addition to that here, so what we do is we are going to calculate what is the maximum shear force developed as a result of the external load. Okay. So how much bent up bars need to be provided if at all we are providing, okay, and what stirrups we need to provide, what are the diameters, how many legs of stirrups, okay, and what spacing we need to give, whether those spacings satisfy all IS recommendations, etc. Okay. In addition to that, we also check for deflection, this one condition here. Okay. So here we design, just we fix the dimensions, we calculate the area of steel, and also we find out the stirrups, okay, to take care of shear. We are going to find out what are the spacings of those stirrups, etc. In addition to that, we are going to check for serviceability limit state, that is for the deflection. Here we are not going to calculate the actual deflection, instead there is some codal recommendation, and once those codal recommendations are satisfied, then we do not have to check for deflection. Okay. That is what the code says is, and that is what we discussed in the first module when we covered deflection and cracking in detail. Okay. So coming to this, so the design, please write down the design of a section consists of determination, of a cross sectional dimensions B by D, where B is the width and D is the effective depth, or capital D. Capital D is the overall depth. So of course we calculate the effective depth in the design, okay, and we are going to add some cover to it as per codal recommendation, and we are going to find out finally what is the overall depth. Okay. Next is determine determination of area of steel. Okay. So both AST and ASC, AST in case of singly reinforced, AST and ASC in case of doubly reinforced section. Area of steel and area and spacing of shear reinforcements. Is it clear to you? So this is what we do. Okay. So we are going to design, number 1, singly reinforced section, doubly reinforced section, and flange section and flange section. So these are the three types of sections. If you again remember what we did in the previous module, so we analyzed these kinds of beams, that is singly reinforced, doubly reinforced and flange section. Okay. Here we are going to design the same. Okay. So in case of, let me take a singly reinforced section. This is what we are going to do first. Design of singly reinforced section. So in case of singly reinforced section, so as I said here, we need to find out what are the cross-sectional dimensions first thing, and also we are going to find out what is the area of steel required. In case of singly reinforced section, yes, as usual, we are going to find out what are the section dimensions needed, and also we are going to find out how much area of tension reinforcement we need. Okay. So here in some cases, or even in majority of the cases, so some dimensions are fixed, not some dimensions of a beam are fixed based on architectural requirements and also based on practical requirements. So sometimes you will be given a beam section saying that beam should be of this much dimension, that is width should be this much, you cannot go beyond that, and they will give the depth restriction because of the headroom problem. They say okay, so beam should be of this much height, you cannot go beyond that. So in such cases what happens is, so we cannot play around or we cannot modify the dimensions. Instead what we can do is we can play with the area of reinforcement within the beam itself. So in case first what we do is we are going to design that beam as a singly reinforced section, and if the moment caused due to the external load, that is the maximum moment caused due to external load, exceeds the mu limit of a singly reinforced section, in such cases what we are going to go for doubly reinforced section. So what do we do in doubly reinforced section? We are going to provide tension reinforcement to take care of the moment up to mu limit value, and any additional moment caused due to the external load coming on the beam will be taken care by providing compression reinforcement in the compression zone, and we are going to balance the compression reinforcement by adding additional tension reinforcement with already existing tension reinforcement. Is it clear to you? That is doubly reinforced section. So here design of singly reinforced section, yes, to fix or sectional dimensions B by D. Okay. If not specified already, Next, I will write this as A, this as B, this as B. So once that is done, then to find out area of tension steel AST. Okay. Next, so to provide stirrups with or without bent up bars. Next, to check for deflection. So what it means? So to fix section dimensions B by D if not specified already. So you will be given a span, okay, you will be given load, or else you need to calculate the load coming on that B. Okay. Based on span, what we do is we are going to fix the dimensions B and D. So what should be the B value? So normally what we do is, if not given, so we have to fix the width of a beam in such a way that this should be fixed in such a way that in order to accommodate the required reinforcement. If we have reinforcement, yes, we have to maintain certain spacing in between reinforcements as per the codal recommendation, and also we have to provide certain spacing, of course vertical spacing and horizontal spacing. Horizontal spacing is the side spacing. Okay. So if the beams are heavy, then the span is too much. In such cases, we are going to go for 2 layers of reinforcement. So, but you don't have to worry about 2 layers of reinforcement. We are going to worry about only 1 layer of reinforcement. So when we are fixing the beam, we have to make sure whatever reinforcement we are going to give should be accommodated within the width without violating any codal provision as far as the spacing between the individual bars and also the side spacing. Not only that, say for example, if B is say 200 millimeter, I am just assuming the width of the beam. So over the beam you are constructing a wall, brick wall, and the wall thickness is say 230 millimeter. So this is 200 millimeter, this is 230 millimeter. So but this is not recommended. So we have to fix the width in such a way that, so if at all a wall is coming, the width should be at least equal to the thickness of the wall, and it can be greater than the thickness of the wall. Okay, that is the way we are going to fix the width. Okay, and as far as the depth is concerned, again we have to fix the depth based on the deflection requirement, but there is a thumb rule. So what the thumb rule says is, if you are fixing the depth, the effective depth should be span divided by 15 to span divided by 10. Okay. By knowing the span, divide that by 15. By knowing the span, divide that value by 10. So you will have two values and select an effective depth somewhere in between these two values. This one, empirical rule is based on experience. Okay. Once you pick up that depth, then you can go ahead and proceed with the design and find out what area of steel required once B and D are fixed. Okay, once the area is fixed, so now dimensions are fixed, area of steel is fixed. Now to provide stirrups. So again, when it comes to the load, again it creates maximum shear force at the supports. Okay, take that maximum shear force and find out what is the area of tension steel at the section of maximum shear force. Based on that, go to table 19 of the code book and find out what is the capacity of concrete based on the percentage of tension steel at that section. Once you find out the capacity of concrete, so whatever shear force we get due to the external load, a part of that load will be carried by the concrete. The concrete strength depends on the percentage of tension reinforcement at that section, and of course depends on the grade of concrete. So we call that concrete strength in shear as tau C. Okay. So as I said, you are going to get that value in table 19. Okay. If you multiply this value by the effective area, that is B multiplied by small d, we are going to get the concrete strength. Okay. So once we have the concrete strength, so whatever the shear force, maximum shear force we are going to get, okay, out of that a part of the load will be carried by the concrete. Okay. Maximum shear force minus concrete strength, you will get the shear to be carried by reinforcement. For the remaining shear, you need to provide reinforcements. So what kinds of reinforcements you can get? So you can give stirrups, bent up bars, combination of these two. See, when you are providing bent up bars, okay, so you must provide stirrups as per codal recommendation. Say for example, to take care of the rest of the shear, if you have bent up some bars, if the bent up bars are strong enough to take care of the shear, still you need to go ahead and provide stirrups. Okay. If you are not giving bent up bars, you can provide stirrups throughout. Okay, I repeat, if you are providing only stirrups, okay, you do not have to give any bent up bars because you are designing the stirrups, okay, to take care of the rest of the shear. Okay, if you are providing bent up bars, so you cannot get away just by providing bent up bars and not providing stirrups. You must provide stirrups as per codal recommendation. And also when it comes to spacing of stirrups, yes, you must follow what the code says is as far as spacing is concerned. It says the spacing for vertical stirrups, it should not exceed 0.75 D, where D is the effective depth, and also you should not exceed whatever the design spacing we are going to calculate, and also you should not exceed 300 millimeter. So get those three values, take the least of those values as the spacing, maximum spacing of stirrups. Okay, least of those three values as the maximum spacing of those stirrups. You will understand what it means once I start solving the problem. Is it clear to you? So next please, after this, to check for deflection. So we are going to check for deflection. To check for deflection, please go to page number 37 of the code book. I hope you are on page number 37. First column at the end, it says 23.2 control of deflection. See, what the code says is you can check for actual deflection, but that is cumbersome. But you can avoid that. So how can you avoid? By checking for the condition of 23.2.1. If you look for cantilever, L by D ratio should not exceed 7, okay, for spans up to 10 meter, simply supported 20, and for continuous L by D ratio should not exceed 26. And of course, for these values we are going to give some modification factors based on percentage of tension steel and based on compression steel if at all it is present, and also for a flange section, that also we can give modification. So these values are modified accordingly, assuming that the span is within 10 meter. If the span exceeds 10 meter, then there is going to be another modification we have to give for these values. So once we check the depth provided to satisfy these conditions, then we don't have to go and check for actual deflection. Okay. So I am going to read out what is given in 23.2.1 on page number 37. It says the vertical deflection limits may generally be assumed to be satisfied. Remember, to be satisfied, provided that the span to depth ratios are not greater than the values obtained as below. Okay. If these conditions are satisfied, then you don't have to go and check for actual deflection. If you are not satisfying these conditions, then you will have to go and check for actual deflection, and we have to make sure that those deflections are within certain limits as per codal recommendation. Okay. So what is the codal recommendation? Again on page number 37, if you go to point A, it says span divided by 250. You know the span of the beam. Okay. When you find out the actual deflection, you know how to check or how to find out actual deflection from module 1. So it says the total deflection. What is the total deflection? Short term deflection and long term deflection. Long term deflection is creep, shrinkage and temperature. Okay. So that is the long term deflection. So in short term, as soon as you remove the center works, that is the scaffolding part for the beam, so due to the external load there is going to be immediate deflection, that is immediate deflection. So long term deflection plus immediate deflection, that is the total deflection, should not exceed L by 250. That is one condition you need to check. In addition to that, you need to separate short term deflection with the long term deflection, and this long term deflection due to creep, shrinkage and temperature should be checked with L by 350, and we have to make sure that that value is within the limits. And also in no case, again if you read out, it says and it should not exceed 20 millimeter, whichever is less. In no case the deflection should be greater than 20 millimeter. Okay. So there are two ways you can check for deflection, or there are two ways you can satisfy deflection requirements. Is it clear to you? So next, write down the effective span 22.2 Page 34, please open. Please open page 34. Write down this figure. So this is the tension reinforcement. This is the cross section details. B, that is the width of the beam, and from the compression edge to the centroid of the tension reinforcement, it is going to be small d. Okay. So this is the support. This is one more support. So this is the face of the support. One more face. So the distance between these two faces of the support is clear span. L stands for span, and I have written clear. Okay. And for this beam, sorry, not for this beam, for this support, okay. So this is the center of the support, and this is where the resultant reaction is going to act upwards. Okay. Similarly, here this is the center of the support, and this is where the resultant of the reaction acts. So what the code says is, in a simply supported beam, L clear plus effective depth, you will get one span, and the distance between the centers of supports, L, C to C. So you will have two values. I repeat, clear plus one effective depth, one value, and the distance between centers of support, you will have another value. Take lesser of those two values as the effective span, and you are going to make use of that effective span to calculate maximum bending moment or design bending moment due to the external load. Okay. So if you are on page number 34, under 22.2 effective span, it says unless otherwise specified, the effective span of a member shall be as follows. So A, simply supported beam or slab. So we are not worried about the slab part. Once we start designing slabs, we will worry about that. So we are going to stick to beams. So it says the effective span of a member that is not built integrally with its supports shall be taken as clear span plus the effective depth, or center to center of supports, center to center of supports, whichever is less. Okay. So it is the effective span it is 22.2 page 34 of the code book. Okay, it says this is not built, sorry, the beam is not built integrally with the support. That means the beam should be a simply supported beam. If you look here, if you assume this as a wall, okay, and of course one more wall, and this beam is placed on the wall, that means these two are not integral. That means they are not put together. So what is the meaning of put integral? That is, if you consider an RCC beam here, sorry, RCC column, okay. So if you are building or constructing a beam here, so the column reinforcement will go like this vertically, and the beam reinforcement will go like this, and depending on the bond requirement, the reinforcement may be bent like this, okay. And we are going to place concrete together so that once we take out all the centering part, then this beam is going to act with the column as a single unit. That means this beam is integral with the column. So in this case, we will have a different effective length. We have to apply a different set of rules as per codal recommendation. But in this case, beam is not built integrally with the wall. Okay, so only worry about this part for your syllabus. Okay, we shall not worry about this. Okay, so this is as per 22.2a. Effective span is lesser of the following two. So what is that following two? Clear span plus an effective depth, that is L clear plus small d, and the next one is L center to center distance. Okay, so lesser of these two values is the effective span LEF, that is small l suffix EF. Okay, so this is the way we are going to fix the effective span of a beam under simple support, that is, it is not built integrally with the support. This is separate, wall is separate, and the beam is separate. Okay, so this is as per 22.2a. Next, when we go to 22.2b, it goes to page number 35, first column. It says continuous beam or slab. Okay, that is not in your syllabus. I am not going to discuss about that. Next, it says about cantilever, that is 22.2c, and 22.2d says about frames. So frames also I am not worried about. Okay, I am going to concentrate on cantilever. So what cantilever class says is, that is as per 22.2c, as per 22.2c, if this is a cantilever beam and if this is the support, if this is the clear span, not the span, length, whenever we come to whenever we come to cantilever, we don't call it as span, instead we are going to call it as length. So L clear is the clear length that is measured from the tip of the cantilever to the face of the support. And of course, we are going to provide reinforcement, sorry, not here, cantilever top reinforcement. Okay, so we are providing reinforcement at the top. This is B, that is the width of the cantilever beam, and D is the effective depth measured from the extreme compression edge to the centroid of the tension reinforcement. Okay. So in this case, when we are constructing a cantilever beam, we are not going to start the cantilever from here. No, we are going to extend this cantilever for stability. Otherwise, the cantilever is going to fail. It is very dangerous. So in this case, what is the effective length? Effective length is, therefore, effective length of cantilever equal to clear length plus D by 2. Okay, that is the effective length of the cantilever in this case. That means, of course, the cantilever extends beyond this. Okay. So we are going to take a distance of D by 2 and we are going to measure the effective length of the cantilever from here to the face of the support. Okay. So what if this beam is continuous? That is, the beam is continuous, this is sitting on a support and there is going to be a cantilever beam. So what it means is, if I consider a beam like this, it's a long continuous beam. Okay. It continues further back. So there is a support here. Okay. So there is a support here. Okay. So from the center of the support to the free end of the cantilever is the effective length of the cantilever. This is L effective. Okay. This is as per, again, okay, this is as per 22.2C. Is it clear to you? And of course, there is one more condition again that depends on the width of the support. So if the width of the support is beyond certain value, then we have to consider a different thing. As of now, you don't worry about that part, simply concentrate on these two. That should be good enough for you. So with this explanation, I am going to go and read out what is given in the code book for 22.2C. That way you can understand what is given there. So I am going to read out that. So 22.2C, page number 35, first column, if you go below, under C it says cantilever. So for cantilever it says the effective length of a cantilever shall be taken as its length to the face of the support plus half the effective depth. That is from the face, this is the face of the support. This is the face of the support. Okay. So take as length to the face of the support plus half the effective depth. Okay. that is from this end to the face of the support plus half the effective depth, where it forms the end of a continuous beam. I am going to read out, sorry, support plus half the effective depth except where it forms the end of a continuous beam where the length to the center of support shall be taken. So in this case, this is okay. So in this case, this cantilever makes the end of a continuous beam. Okay, in this case what we do? From the center of the support to the free end, that is the effective length of the cantilever. Is it clear to you? So please write down these figures and only stick to these parts, and we don't need anything else. So we don't need for frames, we don't need for continuous beam or slab. Okay, I hope this is clear to you. So with this, okay, thank you, and we will continue next.